The objective today is to describe what the Intel manual says about the Eflags register, and before we dive into that, I'm just going to quickly read this segment registers in 64-bit mode section. It's a pretty short section. I should have probably included it in the previous video, but seeing how many modern systems don't use segmentation at all, they use flat address space, I think we can get away with brushing over this pretty quickly, so here we go. In 64-bit mode, those segment registers are treated as if each segment base is a 0. Regardless of the value of the associated segment descriptor base, this creates a flat address space for code, data, and stack. So there's your first question. What creates a flat address space? And the answer is having each segment base equals 0. Now here's something that should look familiar after we studied canonical addressing, but you have this FS and GS register, and these are exceptions. Both segment registers may be used as additional base registers. So my question here is, what are additional base registers for? And I guess that has a lot of answers, so let me just put there that I'm just asking, maybe something for you to bring up to your professor. But both these segment registers may be used as additional base registers in linear address calculations, which is in the addressing of local data and certain operating system data structures. So during the canonical addressing video, we talked about how these are special and kind of strange, and that operating systems, Windows and Linux, they are the ones that are utilizing these not only in two different ways, but two different unintended ways. At least unintended by Intel, that is. Now, while I was reading this, I wrote myself a note to Google operating system data structures. So there's the question right there. I genuinely wanted to know where they were going with that, and based off just a quick Google search, it looks like basically they're referring to queues. The queue is a data structure which is used in almost every operating system, and that's because of an operation called process scheduling. So when another process wants to start, it is put in the queue where it will have to wait for its turn, and the queue is different than a stack in the sense that it has a first in, first out basis. In a stack, whatever you put in last will be the first to come out. So that's called LIFO, or LIFO. So what is an example of an operating system data structure? The answer is a queue. Now, even though segmentation is generally disabled, segment register loads may cause the processor to perform segment access assists. I need that as a question. So there you go. During these activities, enabled processors will still perform most of the legacy checks on loaded values, even if the checks are not applicable in 64-bit mode. Such checks are needed because a segment register loaded in 64-bit mode may be used by an application running in compatibility mode. So my question is, you can run a 32-bit program while running a 64-bit one? In which case, it sounds like the point of this paragraph is that even though segment registers may be disabled for one thing, they can still be utilized by another. So with that said, the section ends by saying limit checks for these registers are disabled in 64-bit mode, and there's another question I seriously don't know the answer for, and that is like, what are limit checks? If we're in 64-bit mode, is there no limit to the amount of bits that these registers can have, so therefore there's no reason to check for them? Well, let's get to the meat of this video, and that is the Eflags register. I like this part. Once I understood that this register is just something that will tell us about the results of something, I really thought that was a good design idea. So they say that the 32-bit Eflags register contains a group of status flags, a control flag, and a group of system flags. So you got status, control, and system. So there's the question, what type of flags are there? In the Eflags register, I should say. Just sounds better that way. So figure 3-8 defines the flags within this register. I'll show you that. That's a pretty complex diagram actually. But let's get the reading done first. It says, following initialization of the processor, either by asserting the reset pin or the init pin, the state of the Eflags register is 00002H. Oh, and for my students who know hexadecimal, they understand that there is no H as a number in the hexadecimal system, so that means every 2 digits right here is a value. A 1 byte value, that is. So right here we have 1 byte, 2, 3, 4. 4 bytes make 32 bits. If we're talking about the Eflags register, we're talking about a 32-bit value. And so I ask, what is the binary value of this register at startup? If it's simply the number 2, so what I say, we have 32 bits, so it's a lot of zeros, and then a 1 and a 0. So maybe it looks more like this. Again, I'm just not going to count it for this video, but here is the value of 2. So this is what that register looks like when you first turn on the computer or initialize the processor, or you reset the processor, as we can see right there. Now bits 1, 3, 5, 15, and 22 through 31 of this register are reserved. Software should not use or depend on the states of these bits. So this bit, number 5, however that works out. And okay, so there's a couple bits. You're going to see that in the diagram actually. So let's just go down there real quick. So seeing these bytes, these bits I mean, at 0, they're reserved for something. Maybe Intel will tell us later, because right now there's no arrow, there's no description right here. So some of the flags in the Eflags register can be modified directly using special purpose instructions. I asked the question, why would we want to do that? Now there are no instructions that allow the whole register to be examined or modified directly. So just to be inquisitive, I asked, like, why can't we do that? What would be the problem? Now, following the instructions can be used to move groups of flags to and from the procedure stack. There's that word again. I've seen this before. I wonder if they mean just like a regular stack. Maybe it's a stack that is holding functions or methods or procedures. Whatever it is, they are about to give us a list of instructions that could be used to move groups of flags from a stack or the EAX register. Now my question right here, what is the EAX register used for? Remember, this is the accumulator. That is, it stores the results of operations. So in the beginning with the 8086 processor, we had a register called AX where the results would be stored, and then later when we doubled those 16 bits to 32 bits, we had an extended AX available to use or store results. So there that is. Now later when we get to 64 bits, we'll have the register AX. I don't know why they called it RAX, maybe to refer to the fact that it's a register. Maybe by going to 64 bits they're like, let's go back to the basics. But for whatever the reason, just know that the EAX register is used to store results of stuff. So maybe they're going to move groups of flags to EAX. And you could do that by using commands such as LAHF, SAHF, PushF, PushFD, PopF, and PopFD. Now, after the contents of the Eflags register have been transferred to the procedure stack, or EAX register, the flags can be examined and modified using the processor's bit manipulation instructions. Now, these are really cool. You can manipulate the bits in either the procedure stack or the EAX register. And by the way, right here, EAX, I went ahead and said the story I just told you over here. I think the only thing I'm missing is that in the very beginning with an 8-bit computer, that accumulator register was just called A. And then when we went to 16 bits, it went to AX, then EAX, and then RAX. The other registers, their names actually make sense, so it's not just alphabetical order, but B is for base, and C is for count, and D is for data. How convenient. So when suspending a task using the processor's multitasking facilities, the processor automatically saves the state of the Eflags register in the task state segment. That's kind of cool. So you get this register for each task you're doing at a time. I wonder if task is another name for a process. It sounds like they are the same thing. And that old task you were working on when, multitasking is being suspended. So if you ever wonder what the task state segment register is, what it's holding what Eflags used to hold. That is actually a really easy way to understand that particular register. And so logically it says when binding itself to a new task, the processor loads the Eflags register with data from the new task's TSS. So I wonder if there's multiple TSS registers. If I have like 10 tasks going on, would I have 10 TSS values? And maybe I'm thinking too high level. we are talking at a very, very low level here. Well, good news, here's the last paragraph. When a call is made to an interrupt or exception handler procedure, the processor automatically saves a state of the Eflags registers on the procedure stack. So I think that's a good question. What two places store values from Eflags? One answer is the TSS register, and the other is the procedure stack itself. So when an interrupt or exception is handled with a task switch, the state of the flags register is saved in the TSS for the task being suspended. Okay, so I think that's pretty straightforward, maybe even redundant there. Let's end the video by looking at our register diagram here. And there is really just not much for me to say here, except maybe to point out little details, like S indicates a status flag. So everything within S here, and over here, the overflow flag, these are status symbols of the result. So if I did something with two numbers and they resulted in a negative number, this sign flag would be a 1. If it's not negative, it'd be a 0. If I added 0 plus 0, the 0 flag would be on because the result is the number 0. Just like if I took 8 minus 8, the 0 flag would be a 1. Else, it'd be a 0. And I'll leave it up to you to figure out what these last three are. For any students who have followed my cybersecurity kind of lessons, you will probably recognize this parity flag right there. And then I just can't help myself. The students who took the hardware class with me, they'll definitely understand what this carry flag is. We created our own full adder in class, and then watched what happened to each of the bits. So pay attention to those S's for status, and you got C for control. There's a direction flag, okay, there's only one control. And then X marks the spot in terms of it indicates a system flag. So system flags are probably big deals. You got I/O privilege level, nested task, resume flag, the virtual 8086 mode, this one probably is rarely on. You have an alignment check, a virtual interrupt, a virtual pending, and then an ID flag. Before I read, I could summarize. Flags have been the same since forever. So they say that as the IA32 architecture has evolved, flags have been added to the Eflags register, but the function and placement of existing flags have remained the same from one family of the IA32 processor to the next. As a result, code that accesses or modifies these flags for one family of processor works as expected when run on later families of processors. And notice this next section doesn't talk about Eflags in 64-bit mode. Intel does a weird thing where they actually put that down here, and when they do, they make it really short. Essentially, it just says that those 32 bits at the lower end is the exact same as Eflags. But the top 32 bits is called R flags, and at least here, it doesn't give us any details about those R flags. So, thanks for watching, and next time we will go ahead and cover status flags.